Today we're doing section 3.1, Introduction to Determinants. Let's talk about some notation right now. Matrix Aij is the matrix obtained from matrix A by deleting the ith row and jth column of A. For example 1, find A, 2, 3, where A is this matrix. So that would mean that we would delete the row 2, because it's the ith row, and that would be the 2, so row 2, and the third column. So A, 2, 3 would be 1, 9, 13, 2, 10, 14, 4, 12, 16. Now let's recall that the determinant of A, C, B, D is AD minus BC, and we let the determinant of A equal A. For n greater than or equal to 2, the determinant of an n by n matrix A is the determinant of Aij is given by the following. So to find the determinant, we can take an A11 times the determinant of A11 minus A12 times the determinant of A12 plus all the way to the last one would give you the determinant of the entire matrix. So let's look at example 2 and use this definition. So example 2, let A be this matrix, compute the determinant of A. So the determinant of A would be, first if I use row 1, column 1, it would be 1 times the determinant of the remaining matrix, which would be negative 1, 0, 2, 1. Minus, now if I do the first row, second column, where it crosses, that would give me a 2 times the determinant, and I'm left with 3, 2, 2, 1. And then the last one would be plus 0, because that is the first row, third column, and I'm left with 3, 2, negative 1, 0. When I go ahead and do this, this would be 1 times negative 1 plus minus 0, which is just negative 1, minus 2 times 3 minus 4, which is negative 1, plus 0 times 3 minus negative 2, or excuse me, 0 minus negative 2, which is 2. This would then equal 1. So the determinant of A is 1. Let's talk about some common notation. Okay, some common notation is I could say, so when I have absolute value around my matrix, 1, 3, 2, 2, negative 1, 0, 0, 2, 1, this absolute value means find the determinant of. So I could rewrite this as 1 times negative 1, 2, 0, 1. That means find the determinant of, minus 2 times 3, 2, 2, 1, and plus 0 times 3, 2, negative 1, 0. All that means find the determinant of A, which would be 1. Let's look at the cofactor expansion across the first row. So when I have the I and J cofactor of A is the number Cij, where Ci is negative 1, to the I plus J times the determinant of Aij. So for example, the cofactor expansion across row 1 of this will be 1 times C11, because that would be first row, first column. So that would leave this matrix here. That's what C11 is. Minus 2 times C12, 1, 2 would give me 3, 2, 1, 2, or 2, 1. And then 0, C13 would be this, leaving this matrix here, 3, 2, negative 1, 0. And that's the cofactor expansion across row 1, which is what we did in the previous example. So theorem 1, the determinant of an n by n matrix A can be computed by a cofactor expansion across any row or down any column. So for example, this would be the expansion across row I or the expansion down column J. So let's look at an example. So example 3, let A be this matrix, compute the determinant of A using cofactor expansion down column 3. So down column 3 means column 3 is going to be crossed out every time. So we'll be going across row 1, row 2, and row 3. So using the definition, the determinant of A would be A13, C13 plus A23, C23 plus A33, C33. Or 0, because that's row 1, column 3, times the determinant of 3, 2, negative 1, 0, minus 2, times 1, 2, 2, 0. Oops. Plus 1 times 1, 3, 2, negative 1. When I go ahead and find the determinant of this matrix, and this matrix, and add all my terms together, I should get 1. So why don't you try that on your own and double check your answer here, and you should get 1. Theorem 2. If A is a triangular matrix, then the determinant of A is the product of all the entries on the main diagonal of A. So let's compute the determinant of A. This is a triangular matrix. It's an upper triangular matrix. So the determinant of A would be along the main diagonal, the product of all those. So 2 times 1 times negative 3 times 4, which equals negative 24.